shared my session, so I'm going to be chairing his session. So, Daniel, take it away.
Hi, I'm Winograd-Cort from Yale University, working with Paul Budek, and talk about virtualizing real-world objects in FRP. So, FRP, functional reactive programming, it's about programming with continuous values, or streams of events, streams of values. And when you do it, it's like you're making a signal processing diagram, you're drawing a box and pointer diagram. So here you can see there's this signal processing diagram with X going in, getting processed, and Y coming out. And we think of X as this stream of data, and Y as another stream of data after it's been through the signal function. And Haskell has this great arrow syntax, which lets us write almost the same thing, and it's Haskell code. So this has already been used in Yampa, Nettle, Interpia for various animation, robotics, music, sound synthesis, networking. So just really quick, I'm going to go over arrow syntax because I know a lot of people don't know it. So we're going to write a small program that integrates a value coming into it. So if you were to write with a signal, or integrates a value and doubles it, right? Do two things, make it more complicated. So you're in a signal processing diagram, you might have something like this. The X is coming in, it goes through the integrator, integral, and then it gets multiplied by 2 and comes up the other side. And I write it from right to left on purpose because when we translate this into arrow syntax, it works the same way. So here, the first line, sigfun, is an SF from double to double, meaning that it's a signal function that consumes doubles and produces doubles, streams of doubles. And then we have some syntax, some notation that says that it's it takes it, the input value is X, and what it does is it sends X through the integrator, through this integral signal function, and Y is the value after that, some sort of instantaneous value between the integral and the times 2. It would be with some this Y or here. And then we multiply it by 2 and return it. And return A is almost like a keyword, it's just a shortcut function for ending the arrow syntax, ending the signal function. When you're programming in FRP, what you often have is something like this. You have a lot of I/O devices, and then inside you have your runtime system with your nice, pure signal function. And this is good. You don't necessarily want I/O going on in the signal functions because you have all these nice purity properties that you can have. And once you introduce I/O in there, you never know what's going to happen. But this still causes a problem. It's this bottleneck that all of the inputs are going into one little spot and then being sent to the signal function and then kind of coming out the other end and going out to the respective I/O devices. And so what we want to do is kind of expand the main program to encapsulate all of these I/O devices. As I said, it could be tricky, but it's going to be nice, as you'll see in a second. So if we move the main program to encapsulate all of them, then all of these I/O devices you can think of as signal functions. So for example, the mouse is a signal function that takes no input and produces a stream of maybe position values or a stream of click events. You could have an electric piano. The MIDI keyboards often have input as well as output, and they just add their note events to the stream that's going through them. And so now you can think of your whole program as these signal functions. And you don't need to worry about, like, oh, how does it interact with the outside? Or how do I, display values at some point? It's all just kind of done together. We don't need to stop at I/O devices. We don't need to stop with a mouse. You can do this with a widget, right? Or something on the screen, something virtual. And you can also do it with non-local effects. So you can even have a random number generator. You can think of it, even though it may have a seed from the operating system, you can use it as a signal function. It's nice to be able to just have your signal functions right there. The problem comes with the idea of purity that we talked about. If you think of your signal function still as being pure, then you want to be able to use them whenever you want, right? You have a function f, you can use it in multiple places. But if that function f is listening to an I/O device, then you can't just duplicate it. You only have one mouse maybe attached to the computer. So if you look at this example, you have a MIDI synthesizer for synthesizing MIDI notes for a musical program. And you feed it a note list, and then you feed it another note list. And it's totally unclear what's going to happen, whether it's non-deterministic or you have some interleaving. You can think of the same thing for a random number generator. If your random number signal function produces a random number, and then you call it again, is it the same random number, or will it get a new one? It's not entirely clear just from looking at code like this what will happen. So that's kind of odd. So what we can do, what I've done is to add this new parameter, which we call a resource type. And it's basically a way to, it's kind of similar to linear types, but it's a way to add a tag that says what this signal function is doing, what resources it's acting on. So our MIDI synth would have S MIDI synth, indicating a singleton set of resource tags, being just MIDI synth. And the random signal function would have the random resource type, indicating that it's using the random seed. And what we'll say is that two signal functions, if you want to compose them together and use them at the same time, have to have disjoint resource type sets. And so that way, the code from the last slide of those two MIDI synthesizers both getting a notes list, they wouldn't even run because you try and do it and you see that your resource type set has two of the same resource type. So we end up doing this with arrows and hierarchy types, type families, functional dependencies. So I'm going to go into that description a little bit of how we made these. Yeah?
So if the program uses the MIDI synth and a random generator, would it have S MIDI synth, S random ID?
Right. I don't show that right here. So there's a U for union. And so the way we build these up is there's singleton sets, there's unions, and then there's empty set.
And you correct MIDI synth being union with MIDI synth.
Exactly. That's exactly right. So you can't use them together. Great. So to implement these resource types, first we need some sort of resource type. We need a way to use them, to put them in, and then we need to restrict composition. Restricting composition is not so easy, but we can do it with arrows because, redefining function application is hard, but we can redefine the arrow class pretty easily. So let's look at the standard arrow class. So these are the main functions that you use. There's some other ones. There's some extended arrow stuff, arrow choice, arrow init. But we're going to focus on these. And all of the arrow syntax is translated into these functions. So without looking, you look at the type signatures, but if we look at this slide, we can see how they work. Air is a function that lifts a regular function into a signal function. First, we'll take a pair and apply your signal function to the first part of the pair. This is compose, and it takes a value, puts it to the first signal function, and then the second one, and outputs it. And then loop is like fix, but for arrows. It kind of loops through a secondary parameter. So really quickly, these inference rules are not very exciting. So arrow, when you make it, it's not going to have any resource types. It starts out empty. First, if the incoming signal function had a resource type, or had any resource types, the output will too. The interesting one, as we've already said, is here. We want to have the intersection of the two resource types be empty for composed two resource type sets. And we want the output to be the union. And then loop is also not very exciting. Just whatever is being looped is going to remain with those resource types. So now we get to some type code. This is what would happen when you add in the resource types to the arrow class. You see now arrow takes 3 arguments, R for resources, and then the B and the C. And the most exciting thing here, obviously, is this disjoint and union thing. So we're going to go into how those work, because that's kind of interesting. So first of all, as I said, we have these 3 ways to make resource type sets. Make sets at the type level: empty, singleton, and union. So unioning is easy because we have this U. There's slightly more work for the actual union So there's a little bit of work there, but it's pretty straightforward. Set disjointness is more complicated though. So here's most of the class of disjoint x's and y's. And so what it basically says is that if you're that anything that's empty is going to be disjoint with the other argument. And then if you have a singleton set, then it's going to be disjoint with the other set as long as that item in the singleton is not in the other set. And lastly, you can know if a set is a union, then it's disjoint with the other set if both of its two constituents are disjoint. So this is great, but LM of is still kind of tricky. We want to know that a resource type, or a type is not in the set of resource types. So we need to do this set membership. So we have a functional dependency. We use these Boolean types that would, in the future, be done with the new kind system, but obviously I haven't done that yet. And so now, once again, X is going to be a resource type, and it's going to be in the set or not, given by the Boolean output value. So X is never going to be in the empty set. That's pretty clear. And X is in the singleton set if it's equal to the singleton element. And X is in the union if it's in either of the pieces. So OR is a pretty straightforward type class to do. That kind of structure, the OR and the AND and these Booleans, come from the H-list package, so I'm not going to go into that very much. Except for type equality, which we still have to do and is tricky and is kind of a clever hack. It uses type families for the type equality, and it uses functional dependencies, and it uses overlapping instances. And it really has to make use of all of this stuff to get around the compiler just a little bit so that you can tell whether two types are equal. Simon doesn't really like it. Hopefully there will be a better way eventually.
There will be a better way.
But for now, this is what we have to do. Kind of a pain, but it finally ties everything together. This is the linchpin on which the rest of this stuff stands. So now that we have this idea of resource types and ways to kind of union them and check for disjointness, we can make a signal function type, which is just an instantiation of the arrow. And the way we're going to do it is a pretty standard signal function representation, same thing that's used in Yampa mostly. And what this says is it's just going to take a value and return the next value in the string plus a new signal function to produce more. So it takes the resource type, so the type arguments of the resource types and the input and the output for the signal function. And you can turn this into an instance. It's actually really straightforward. This is basically, there's the automaton arrow transformer, and you also have this hint of this Kleisli arrow, and they just kind of go together exactly as expected. The implementation matches the type pretty nicely. Great. So back to user level. That was all kind of the inner workings. So how do we make these SFs? So we're building them out of I/O, and we want a user to be able to make their own signal functions, make their own resource types. So a resource type is just an empty data declaration. It's just literally a type. And so when you make them, you can use these nice little shortcuts, the source, sync, and pipe, to turn an I/O action into a signal function. And they were kind of expected, right? A source is going to create a value. So if you have an IOC where you're reading some value from I/O, then it's going to turn into a signal function that takes nothing and takes unit and returns that value, or a stream of those values. You'll notice that whenever we use source, sync, and pipe, it has to be a singleton, and we require that because we want the user to not try and have a whole bunch of resource types all at once, but also not to leave it blank. If you're doing an I/O action, you should be marking that you're doing it. And there's no real way to make someone mark it, but we can, if you use source, sync, and pipe, then you're required to put something in there. And then the event-based ones are similar. Event is basically like maybe. It's either an event on the stream or it's nothing. we can easily define them. This is just in terms of the stuff we saw on the previous slide. And it's just going to, once again, it works pretty much how you expect it to. So with source, if you have some I/O action, then what it's going to do is it's going to do that action and return the value that's created plus the signal function again with that I/O action ready to go. So that's here. The value plus the signal function with the same function and the same approach. Holds the same for sync impact. The event-based ones are more interesting. I don't think I'll have time for them, so I won't get into them. But they involve spawning new threads. So if you have, say for some reason you wanted to do put string or get char as a signal function, well that blocks, and you don't want that behavior. So what you end up doing is you lift that into a separate thread and make it an event. And so now nothing will be passed through continuously unless there's data coming from that action, and then an event will be generated. That's how you would create source of events. So going back to that mini-synth example for just a second. msynth would take some, it might be the monadic action for that, that signal function, take some nodes, produces some I/O. Using resource type SFs, we can just do sync E of msynth and say that it uses the mini-synth resource type. And that's great. And now our example from before doesn't even time check. It just stops right there. We have to do something else if we want to have those two node streams. We have to manually interleave them or do them in an order that we define. So you can do it for virtual objects too. Utopia is this music writing language, almost kind of a sub-language of Haskell, or more like a library. And it has its own graphics library, its own widgets. And because this research, this idea was based on Utopia and working with these like MIDI keyboards and whatnot, I built resource type signal functions off of the Utopia UI. So this is how you might define these things. You simply create them. H slider makes a horizontal slider. Title gives it a title. The real-time graph plots data that you give it. You define what their resource types are going to be, and then you go. So here's this function that just makes a graph of a sine wave, given a frequency and an amplitude, and run it for you. It's basically that simple. It's a little bit more complicated because I don't, yeah. So that's basically what it looks like. And you can adjust the frequency, the amplitude. Yeah, cool. That's basically all it is. But it's good. A pretty simple program. It's got flow exactly as you'd expect. You're grabbing data out of your sliders, you're feeding it into this frequency to sine function, and then you're graphing it, which is nice. And if you look at the type, I use a nice little type synonym. I think that should be capital, but it's not. But you can see that it tells you exactly what you're using. You know exactly what you're touching. So it doesn't necessarily say I/O, but you do know that it's using 3 widgets. Oh yeah. So let's say we wanted to see some debug data. I didn't actually show you the internals of freq to sine, that little function. But if we had some debug data that we wanted to show, we would have to do something like this in a regular signal function. And this sucks, because now everything that depends on freq to sine is going to fail to work anymore. Because instead of just returning a double, which was the answer, this second double is the debug value. That's a real pain. Even our original graph function is not going to work that we just wrote. So what we can do is use a wormhole. Wormholes are fun. They are basically just a mutable variable in memory. And you put stuff in one end and you read stuff from the other. And we call that a white hole and a black hole. Because the black hole is a bottomless pit that you can't get anything out of, and the white hole spews up data for you to use. And so because it's basically just an I/O graph, in fact, here it is. It's just an unsafe perform IO of an IO ref that we source and sync. But what's lovely about this is because of our resource types, we can be assured that you're only ever using this appropriately. There's only one place you can possibly read from it, and one place you can possibly write to it. So it's kind of a guarantee right there that you're not going to write to it and then accidentally write to it somewhere else. Or read from it and then use that value as if it were new somewhere else. Yeah. So we can create a nice little wormhole. Yeah.
Sorry, I was just saying.
Oh, wow. That was a question. We create a nice little wormhole, and now we update our freak to sign function, and you'll notice its type does change, but not in a structural way. These resource types have no runtime value. They're just there for type checking. So now it's marked as saying it's using the debug black hole, and it's kind of a note, almost like a comment to someone reading this, saying that there's some debug data in the black hole that's ready to be read if you want. So our old sign graph function totally still works now. It's got a slightly different resource types, but the content of the program still works. And we can make a new one, sign graph with debug. We create another one of these real-time graphs because we want to graph the data. And that sign graph with debug has both the debug wormholes, the original sine wave resource types, and the new debug graph resource type. And you see how it works. It runs the sign graph, and then it looks at the wormhole to see what the sign graph has produced, and it sends it out to a new graph. I can run that one too. Great. And actually what I'm plotting is the exponentiation of the frequency. So you can see in the debug down there. That's really all it is. Wasn't that exciting? There wasn't much exciting debug values to show here. But you could put anything in there and it would work like this. Cool. Yeah. Okay. So there's still a bunch to be done on this. One big thing is signal functions in parallel. So I mentioned this idea of event-based stuff and moving it out to another thread to run it and then waiting for values to come in. And that actually works really nicely. And so if we push the work from a signal function out into other threads, and then we can use something like a wormhole. I don't know that that's actually thread safe right now, but something thread safe like that, then we can use those resource types to kind of restrict the communication between different threads and monitor it in a really nice way. So I'm going to look into that. Rebindable syntax for arrows. So arrow notation doesn't actually work yet with resource types. All the code I've shown won't actually work because it barfs on the resource types. So you have to run it through a preprocessor first, and then give it to GHC. So I'm going to fix that. I'm going to add rebindable syntax for arrows to GHC. And then the last thing I'm going to look into is local resource types. You may have already noticed with that little program that it had like 6 resource types all union together. If you have a big program that uses 10 wormholes, that's 20 resource types right there, not including other things you can be doing. So getting some sort of existential types or local types of some sort, or some sort of technical counters so that you can keep track of a group of widgets, say, would be really nice. So just to wrap things up, resource types are nice because instead of just having I/O, which doesn't really tell you what's going on, they tell you exactly what you're using, and they restrict the functionality to exactly where you're using it. They give you these non-local effects, these wormholes, that you couldn't do in single functions before because they were dangerous. And with the resource types, it makes them a lot safer. And they're straightforward to program with, once I get the arrow syntax working, of course. Yeah. So that's it. Questions? Yes.
Questions? It's a very nice work. It takes pain away from writing this Reactive function. Yeah, but I have this question. So this sync and source functions that you showed that leaves these IO actions into signal functions. So are those functions supposed to be used by users or just FRP library writers?
So depends how, well, basically they're supposed to be used for FRP library writers. So if you have devices that you want to support, then you can use those functions. But I mean, you could imagine a user who has physical devices that they want to put into their program. So if they have 3 mini keyboards and you've written support for 2 in your library, then they can say, well, I have another source here. It's another mini keyboard. And I'm going to wire it up to another piece of your library and stick them together. And I know that that'll work because I have 3 distinct resource types here.
So it's their responsibility to give correct time to whatever new resource.
Yeah, so that's one of the big limitations here is that we can't really force people to do these things properly. We can hope, and but it's hard to enforce. Yeah.
Can you do dynamic queries, like every time you press a button it adds a new graph, so you just kind of accumulate graphs?
Right, so not exactly. So when you make a resource type, it's just a data type. So you need all of the data types ahead of time. You have to make them statically. That said, you can make, for example, for widgets, you could make a set of widgets that's a dynamic set, dynamic number of them, and give it one resource type, which is your set of sliders. It kind of breaks the idea. We'd like a much better way to do that. But with widgets, using resources is more an idea of tagging the I/O as opposed to keeping track of individual widgets. So that's the best approach we have right now.
Can I ask one? So basically you need rebindable syntax because your arrow class is not the standard arrow class.
Right. So because we added those resource types, yeah.
Yeah. And have you formulated arrow laws for your version of arrow class?
So not exactly. The short answer there is that our arrow class is at least as restrictive, right? So I mean, basically all of the arrow laws that already exist should remain with this because we're only restricting more. So we haven't actually done the work of figuring out if there are new laws that are nice, but all the ones that are already there should hold. So taking something that's already an arrow and lifting it into resource types is very straightforward. You could take, for example, a regular function application and give it an instance for the resource type arrows, and just every function would have empty, basically. And that's fine. In fact, we have a nice type synonym for that to say that it's a pure arrow now. And that's kind of the indication that it's not I/O. Or actually, it's a generic monad that happens to be I/O in this case. You could use a different one.
Any other questions? Thank you,